Right. In today's session, we're going to be talking a little bit about some formalities and some alternate ways to talk about the measurement of angles. Um, Before we dive into this, I do want to stress that on the Google Classroom site, along with this video, is posted a document to go along with this. This is material that isn't in your textbook. It is coming out of this alternate document. Basically, the ultimate document is part of the Pre-Calculus 12 textbook. A year or two ago, the province decided the order of things needed to switch up a little bit. So these next couple of sessions are coming out of this alternate material. So if you haven't got the material along with the uh, link to the video in your Google Classroom site, you should go and make sure you can get a hold of that now. It's a PDF attached to the same post in the stream where this link to this video was posted. And when I refer to examples in this session, it'll be examples coming out of that alternate material that was posted along with the video link. Okay, so getting back into it, we are talking about angle measurement and a couple of formalities around that. Um, One thing that I want to stress to start with is that, we're used to thinking about measuring angles in degrees, and most people can picture what a 90-degree angle looks like in their head, or a 45-degree angle, and that sort of thing. Um, but it's a fairly arbitrary way to define an angle. We kind of base it on the fact that, well, the definition that there are 360 degrees in a full circle. If you thought about it as a rotation, it would be a 360-degree rotation. Um, and where does that come from? Where do we get this definition that there are 360 of these things in a circle? There's different thoughts on where this might have originated. Some think it may have come from the Babylonians. The ancient Babylonian calendar only listed 360 days in it, so 360 days would make a full cycle of a year, which, if you have a calendar laid out in a circle as the Babylonians did, meant you'd have 360 divisions in the circle, 360 degrees. Um, that's one theory on where this may have come from, but all in all, it's a fairly arbitrary definition, and it turns out we have a much more intuitive way to define this. And it comes back to this thought of what exactly pi is. So, we'll talk a little bit about pi. What is pi? Pi is the ratio of the circumference of a circle, I should say of any circle, to its diameter. And this is true for any circle. If you take any circle and you divide its circumference by its diameter, you get pi. Straight out. That is what we define pi to be. And based on that definition, we can say the circumference of a circle is equal to pi times its diameter, or pi times twice its radius. In more simplified form, we'd often see circumference equals 2 pi times r. So, what does this have to do with measuring angles? Well, we'll get there in a moment. First, a little bit about arc length. An arc is a segment of a circle, and in the most predictable definition in the world, arc length is, oh, wait for it, the length of an arc. Oh, hold on, take a second. Breathe. This one's pretty rough. Arc length. The length of an arc. Woo! So if I've got a circle, roughly speaking, an arc would be some section like this. That would be an arc. And we often symbolize arc length with an S. I don't know why. So, what makes up the length of an arc? So let's say I show it in this form. I've got some radius of a circle, and the arc has been created by two radii forming an angle theta. A couple of things that I can say. The bigger r is, or the bigger the radius is, the bigger that arc length will be. And the bigger that angle is, the bigger the arc length will be. The larger r is, the larger the arc length will be. And the larger theta is, the larger the arc length will be. Now we try to say that a little bit shorter when we're talking mathematically, and what we basically say is that S is proportional to R and theta. Which basically means what I wrote above. The bigger R gets, the bigger the arc length will be. The bigger theta gets, the bigger the arc length will be. Now, there is one arc length that we have been talking about, or you've been talking about in math class for quite a while now. That is the very special case when your arc is the entire circle. We call that particular arc length a circumference. The circumference is a special case of arc length. And let's compare these two for a minute. So if arc is the whole circle, for an entire circle, S equals 2 pi r. But I know that my arc length has to be proportional to the angle and the radius. It looks like I could set up a direct correlation here if I base my angle on pi. And that is the basis for what most mathematicians would use for angle measurement. And that is what we call radians. If we allow so I say this. If we allow our angle to be measured in terms of pi, we say an entire circle takes in 2 pi to match up with our statement for circumference. Terrible. Then we have the basis for what we call radian measure. And I do want to stress this thing that we're introducing, this radian, is just another way to measure an angle. The same way that inches and centimeters are just two different units to measure a length, degrees and radians are just two different ways to measure an angle. They can be converted back and forth. Radian measure and degree measure both are measuring the same thing, just using different units to do it. The reason we talk about radians is because they have a bit more of a basis in math, where a degree measurement is a bit arbitrary. Although, being human, we tend to picture our numbers a little bit more easily in nice, easy to count units like whole number degrees rather than radians, which are often measured in multiples of pi. But the topic at hand. Radian measure. From what we talked about before, we would say that 2 pi radians would be equal to 360 degrees. And that's the basis for us converting these units back and forth one to the other, from radians to degrees and vice versa. Also worth noting, arc length, S, would now be equal to r theta, assuming theta is measured in radians. Okay, I'm going to go through a few examples of working with this radian measure. Mostly it's just going to be conversion based, going back and forth from degrees to radians and so forth. So from that extra package that is attached to, or is linked to in the Google Classroom, this is example 1 from page 168 of that extra material. And it's just basically asking us to convert things. A is convert 30 degrees to radians. This relationship is going to be the basis of our conversion. And much the same way as I'd convert anything else, I'll set up a ratio to multiply by. 30 degrees times 2 pi radians over 360 degrees. Since 2 pi radians and 360 degrees are equivalent, then this is just the same as multiplying by 1. But when I multiply across, my units in degrees will cancel out, and I would end up with 60 pi over 360 radians, which reduces to pi over 6 radians. Note, if you see an angle measure without units, it implies the units are radians. So in this case, my leaving a unit off of this is on purpose, because it's an angle measure, and without a unit, it's implied that's in radians. I should also note, if you took your calculator and worked that out, you're not getting an exact value, you're getting an approximate one. And you would have something like pi divided by 6, or approximately 0.52 radians. So this is an exact value, and this is an approximate value. That will make a difference for sometimes what you are asked to do. B, negative 120 degrees. And I'm going to talk about positives and negatives and angles a bit more in a moment, but basically it would have to do with direction of rotation. So if I'm converting this, I would take negative 120 degrees and multiply it by 2 pi over 360. Some of you might note that this would reduce to the same as pi over 180. If you're comfortable with that and use that, go for it. Multiplying across, I'd get negative 240 pi over 360. I could cancel out the degrees. And the fraction in front, 240 to 360, reduces to 2 to 3. So this would be the same as negative 2 pi over 3, which would be approximately equal to, my handy dandy calculator, 2 pi over 3, negative 2.09. Again, exact value and approximate value. C and D ask us to go the other way. Convert 5 pi over 4 to degrees. And again, since there's no unit put on this, we assume it's in radians. So I would take the 5 pi over 4 I have the same ratio to work with, but now I want my degrees to be my unit that comes out on the other end. So I'm going to reverse the direction of it. You will notice that if your initial angle in radians is stated with a pi, then your pi's cancel out in conversion. And this ends up being 1800 over 8 degrees, which would reduce down to, 1800 divided by 8 is 225 degrees. In this case, my exact answer would be the one to work with, because there's not really any approximation for that. It just works out to exactly 225 degrees. And indeed, they ask you to convert 2.57. And then you say to yourself, wait a minute, that's not shown as a degree, but it also doesn't have a pi in it, so which is it? If there is no unit given with it, it is in radians. Often, radians are stated in terms of pi, but not always. They do not have to be. So this is 2.57 radians. So I convert it the same way I converted from radians before. I multiply by 360 degrees over 2 pi. I don't think there's going to be any particularly nice answer for this. It would end up as 462.6 over pi degrees. In this case, usually we would use the approximate value of 147.25 degrees. All right. Now, coming back to arc length for an example. This is example 4 out of that same supplementary material. 4 from page 173 of the extra material. And in this example, we've got Rosemary taking a course in industrial engineering. For an assignment, she's designing the interface of a DVD player, for those of you who remember DVD players. In her plan, she includes a decorative arc below the on-off button. The arc has a central angle of 130 degrees and a circle with a radius of 6.7 millimeters. Determine the length of the arc to the nearest tenth of a millimeter. So effectively, I'm dealing with an arc. That would be part of a circle whose central angle, meaning the angle made by the two legs of the two radii of the circle, is 130 degrees, and the radius is 6.7 millimeters. And we are being asked to find that arc length. Hey, we know S equals R theta, so it's all pretty simple, except, and I want to stress this, the angle must be in radians for this formula to work. So I have to convert that 130 degrees to radians. 130 degrees times 2 pi over 360. It's 260 pi over 360. 36, 13 over 18. And I'm probably going to leave it in terms of pi for me to do the calculation and then round at the end. So my arc length would be 6.7 millimeters times 13 pi over 18 radians times 13 pi over 18 to get 15.2 millimeters rounded to the nearest tenth of a millimeter as the question asked. The length is, I should say that's approximately, okay, moving forward, I'll talk a little bit about how we report angles. And that gets into the notion of coterminal angles and rotation. Alright, so let's say that I've got a nice little setup to show an angle. And I want to show an angle in standard form of 30 degrees. Something like this with a 30-degree angle. So this is 30 degrees in standard position. Now let's say I want to show 390 degrees. And we start to think of this in terms of rotation. A 390-degree angle would basically have you going through one full rotation and then another 30 degrees past that. And look a little awkward, but this sort of thing would do it. This would be 390 degrees shown in standard position. So you might start to notice that as you go past 360 degrees, you start to get angles that look a lot like each other. In fact, the terminal arm for 30 degrees and 390 degrees is located at the exact same spot. And that's where we get into this notion of coterminal angles. I would say two angles are coterminal if they're, I should spell there the right way, if their terminal arms rest in the same spot. And so, for example, for what I have just shown, 30 degrees and 390 degrees are coterminal angles. Now it is worth noting positive angles denote counterclockwise rotation, and not too big a shock after that, negative angles denote clockwise rotation. And for an example of that, negative 330 degrees would also be coterminal with 30 degrees and 390 degrees. And then you might say to yourself, well, couldn't you just keep going with that? Couldn't I just either keep adding or keep subtracting 360 degrees and keep getting coterminal angles? And you absolutely could. And because of that, we bring in a set of notation that lets us talk about all angles coterminal with a particular angle. Generally, 30 degrees plus or minus 360 degrees times n, where n is any natural number, lists all angles coterminal with 30 degrees. So in this notation, effectively n is taking on the value of every natural number. So what does that mean here? That means if n is 0, I have my 30 degrees. If n is 1, I've got 30 plus the 360 degrees, 390, or 30 minus the 360 degrees, the negative 330. When n is 2, I get another full rotation in each direction. When n is 3, another full rotation, and so on. So this is called general form. I'll make sure I use the same. Yeah, general form for reporting angles. And I'm using plus or minus 360 degrees here since my angle is in degrees. If my angle was in radians, I'd be plus or minus 2 pi times n. Okay, a few examples of working with this notation. This is example 2 from that extra material. Page 170. When you are asked to determine one positive and one negative angle measure that is coterminal with the angle given. So for 40 degrees, basically I add 360. 400 degrees would be coterminal. And I subtract 360 degrees. Negative 320 degrees would be coterminal. And there is one positive and negative angle coterminal with 40 degrees. We're also asked which quadrant does the terminal line lie. Since they're all coterminal, they're all going to be in the same place, and 40 degrees is in quadrant 1. Part B, negative 430 degrees. So if I add 360 to that, I'm still going to be in the negative side of things. So negative 70 degrees would be coterminal. Now, if I want to get up into the positives, I'm going to have to keep adding 360 degrees. So I add another 360 degrees to this and get 290 degrees, which would also be coterminal. It's all about adding and subtracting multiples of 360 or 2 pi if you're working in radians. So if I think my way through this, 290 degrees would be in the 4th quadrant. So that means they all have to be. In part C, I'm looking for things coterminal with 8 pi over 3 radians. Now, I'm working in radians, so instead of adding and subtracting 360, I'm adding and subtracting 2 pi, and I will show a little bit more work for that. So, 8 pi over 3 minus 2 pi. That would be the same as 8 pi over 3 minus 6 pi over 3, or 2 pi over 3. So that would be a coterminal angle measure in radians. Now, if I want to keep going and get a negative number, I'm going to have to subtract another 2 pi. 2 pi over 3 minus 2 pi would be the same as 2 pi over 3 minus 6 pi over 3, or negative 4 pi over 3. That would also be coterminal. Now, all of these, you might want to convert this to degrees to figure out which quadrant that it's in, but if you do the conversion, 2 pi over 3 works out to 120 degrees, which is in quadrant 2, and since they're all coterminal, they all have to be in quadrant 2. If you converted them to degrees, this would be 120 degrees, this would be negative 240 degrees, and this would be 480 degrees. One more example I wanted to look at, and that shows more of the general form. And this is from that extra material, example 3, on page 172 of the extra material. And in part A, we're asked to express the angles coterminal with 110 degrees in general form and identify coterminal angles that lie between negative 720 degrees and positive 720 degrees. So, coterminal with 110 degrees generally would be 110 degrees plus or minus 360n, where n's in the natural numbers. So there's the first part, and that describes all angles coterminal with 110 degrees. So for angles between negative 720 and 720, I just start adding and subtracting 360s. So 110 works. If I subtract 360 from 110, I'd get negative 250. If I subtract another 360, I'd get negative 610, which is still within my range. But if I subtract another 360, I'd get negative 970, which is outside my range, so I don't count it. And then I start adding 360s. 110 plus 360 would be 470. If I add another 360, I'd get 830, which is also too far. So these are my angles coterminal with 110 degrees that are between negative 720 and positive 720 degrees. In the last part, same sort of question, but working with 8 pi over 3. So coterminal with 8 pi over 3 generally would just be 8 pi over 3 plus or minus 2 pi n, where n's in the natural numbers. And then I look specifically for values between negative 4 pi and positive 4 pi. So then I put some things together. 8 pi over 3, always going to work. If I subtract 2 pi from that, like I did up above, I get 2 pi over 3, which works. If I subtract 2 pi from that, I get negative 4 pi over 3. If I keep going and subtract another 2 pi from that, I'm going to have negative 10 pi over 3. By the way, this would be the same as negative 12 pi over 3. And if I keep going, I'd end up at negative 16 pi over 3, and that's too far. And then I start adding. If I add, I would get 14 pi over 3, and since this is 12 pi over 3, that's too far. So these are my angles coterminal with 8 pi over 3 between negative 4 pi and 4 pi. Okay, that's about all I have to say about that. There'll be some questions along with the posting in the Google Classroom, and if you haven't already, don't forget to get that extra material that I've posted along with it. Alright, thanks everybody.